Okay, welcome to sampling. This is going to be a big one. There's going to be a lot of math. So I really want to encourage you to take moments to pause throughout this video. If you're not understanding something, rewind the video and watch that section again, because this is going to be pretty intense. So, but it's one of the most important things. So hopefully I will explain it clearly enough that it will be really, really easy for you to get, but just a warning that it's a little bit of a hard one. So feel free to hit pause if you want to put this in your notes in terms of what we're going to cover. So what is sampling? What do we mean when we say sampling? Well, we got to get people to study if we're doing some research. Sampling is a method that lets researchers infer information based on taking a little slice of that information, because we need to get people that make sense for what we're trying to argue. If we want to talk about what all American adults think, well, we need to get a good approximation of American adults. Now, we do have the census. So you probably are familiar with this term census, that, every so many years a country will go and collect information from everyone in the country. And censuses are incredibly important. A lot of things are based on them, like political representation, allocation of funds for schools, that sort of thing. But the word census also means any data that's collected on the whole population. So for example, a census could be all 1,200 actively practicing cosmetic surgeons in Canada. Okay, so census, when we say the census with a capital C, that usually means like a country's census, but census can also just mean collecting data on the whole population. But it is really hard and really expensive to collect data on the whole population. So instead we sample. We just take a little slice. When we take a sample, we're using this to make inferences and predictions about what would happen if we knew about the whole population. So an inference is a conclusion about a parameter of the population based on data from a sample. We really want to try in our sampling to be able to establish generalizability of findings in quantitative research. But in qualitative research, it's usually trying to find people to study that will give the meaning of their experiences. So here's another place that you might want to pause and make sure that you take good notes on all of these terms, because these terms are going to come up again and again, not only in this module, but in the future too. So again, population's just the complete collection of data or people. It's not always people though, it could be other stuff. So for example, you could say an air quality monitoring draws samples from a population of air, like a city's air shed. Or if you give a blood or a urine sample at the doctor, it is a sample of the total population of your blood or your urine. The sample is just a subset or a portion of people or elements selected from a population. The target population is the population to which you want to generalize sample results. So for example, if I'm trying to make an argument about all American adults or all UW-Com majors, it's kind of similar to a conceptual definition in measurement, and it should be spelled out in detail. You should be really explicit about exactly whom you're making claims about. The sampling frame is what is created to sample the target population. It's like a list or a rule. This makes it similar to an operational definition in measurement. So for example, if my target population was UW-Com majors, well, maybe my sampling frame, I go down to the advising office, and not that they would give me this, but hypothetically, they give me a list of all the communication majors. That would be my sampling frame. Or if I want to, and my target population is residents of the U district, that I can get some sort of list from the government of all the U district residents. A parameter is what a variable would look like if you were able to know how it actually exists in the entire population. So, for example, average income for every household in Washington state. A statistic is what the variable looks like in the sample that you have drawn for your research. So again, hit pause if you want to take some notes on these, or if you want to combine your notes from the lecture with the notes from the textbook or whatever. But these are all going to be really important. So something you can think about is like, what is a good sample? What do we want from a sample? Well, the most important thing is that we don't want there to be bias in our sample. And we especially don't want bias that was something that was intentional, like we screwed up or we did something on purpose. And definitely we don't like it when there's systematic bias, like if we miss an entire group of people because of something we did. We also really want something that's going to represent the population of interest accurately and fairly. So representativeness is an important concept, and I want to make clear that we're going to be talking about both the idea of representativeness and generalizability. These are kind of related, so make sure in your notes that you're keeping these clear. Representativeness applies to samples and generalizability applies to research findings, okay? So samples can be representative or not. Representative is what we aim for because we can draw conclusions that are valid for the entire population. So if my sample of U District residents is a good representation of what all U District residents look like demographically, etc., then it's representative. However, if my sample of U District residents was just like the first 5 people I found walking down the Ave, that's not going to be representative. Why do we want representative? Because that makes it high in external validity. And you might remember in the past module, I talked about how we get a little confused with this term validity, because when we're talking about it with measurement, we're talking about measurement validity, how well a measure actually measures what it's supposed to represent. External validity doesn't have to do with measurement. External validity is the degree to which research study results can be generalized beyond the scope of the individual study. So if I do a study of all Canadian adults, did I do a good job sampling that it was representative, so therefore someone can look at my study and say, oh yeah, for sure, those findings that that person had about those Canadian adults would totally also apply to all Canadian adults. So external validity is really important in a study, and we'll talk about this a lot more when we talk about experiments, but remember, it's different than measurement validity. Generalizability is about the findings. It's the ability of the observations made from the sample to closely match observations that would appear if the researcher had been able to study the whole population. We will talk about internal validity later, but basically it's just the internal consistency within the study being good, like all the procedures were done well. Don't worry about it just yet though. To achieve a representative sample, we usually have to use randomness. Random means that all members of the sample are chosen in a way so that everybody in the population has an equal chance to be studied. If you don't have a representative sample, if we don't use random sampling, the chances are that the sample is going to be biased. Representative sampling is not always required, especially not in qualitative research. However, it is sort of our gold standard for quantitative research. Now, it's important though to know that with random sampling, even though it should hypothetically be representative, sometimes it's not, especially when you have people who are minoritized. This means that groups that are small in number, often these groups face discrimination, oppression, or has less access to power in society. But there's also minoritized groups that even if they're not small in number, they still face discrimination and oppression. When you are sampling, even if you're attempting to have a representative sample, sometimes you can make a greater effort to make sure that minoritized groups are better represented in your study. So for example, you can engage in oversampling so that you try really hard to select participants who are in minoritized groups so that there are more of them in the study. You can also engage in weighting. I do this a lot in some of the studies I run, that you adjust the values in the data so that even if you didn't have in your sample enough people of a particular demographic group, that it's proportional to what they actually are in the real population, you give their answers more weight in the study. You basically multiply the data by a certain value. So those are ways that minoritized voices can get more attention in a sample. All right, now I'm going to talk about probability. This is going to be a big one, so if you want to pause this and take a quick break, that's fine, because the next stuff we're going to get into is really, really math heavy. If you took probability in high school or even took it now in college, that's great. If you didn't, I'm going to try to be as gentle as possible. But if you want to pause for a minute, that makes sense. So I'm going to go into more detail about this as we go through this lecture, but I just want to get this idea in your mind about sampling error more broadly. Sampling error is the difference between the result that we get from our sample and what the real true value is in the population of interest. We can also look at this as how sure or unsure we are that our sample represents our population. Now, sampling error, I know the word error sounds bad, but sampling error isn't bad. It isn't a flaw or a mistake. It is inevitable, and it's just the price that we pay for not talking to or getting data from everyone in the population. It's just something we have to deal with. So what impacts sampling error? Sample size, we're going to talk more on this later, but usually a bigger sample means smaller sampling error because they'll be more representative. But we don't want to have a huge sample because it's going to be expensive. So that's a consideration. The variability of the population. Are people really similar to each other or really different from each other? If people are really different from each other, if it's a very diverse population, our sample isn't probably going to be as easily representative. And then the sampling method used, probability sampling, which means that we select randomly from a list of people in a population. It requires a list. Reduces sampling error because everyone has an equal chance of being selected. Okay, probability more broadly. It's just the odds or chances that something will occur. You probably remember this from school. Even if you didn't take a specific probability course, you probably at least know this. Probability sampling is the primary way that we ensure representativeness of a sample, and probability sampling is based on random selection. Again, so that every case has an equal chance of being selected in the population, and that the chances of selecting one person or case are independent of the chance of selecting another. The selection cannot involve any human judgments to avoid bias or influence. So if you use probability sampling that you involve random selection, you can apply probability theory and formally estimate how likely it is that whatever you're seeing in your sample is also going to be true for your larger population. So the probability distribution is a function that is describing the likelihood or probability of different outcomes. So the classic example, you have a 6-sided die. That's the singular for dice, if you didn't know that. The probability of rolling a 1, a 2, a 3, a 4, a 5, or a 6 is 1 out of 6, right? What's the probability of rolling a 3? 1 out of 6. What's the probability of rolling a 5? 1 out of 5, or 1 out of 6, sorry. So we know that, and this builds on that. If you use probability sampling, you can apply probability theory to estimate what you had in your sample is also going on in the larger population. Because it's so difficult to measure the whole population and get population parameters, we instead use large random samples to estimate population parameters. We get sample statistics. We get the values of the characteristics that we care about in the sample population. So imagine I want to know how many votes a candidate named Betty Wu is going to get in an election before the election takes place. The election itself is a census, right? It's like the whole population of people that vote in that election. But I can't take a full census before the election because who knows, maybe someone's sick that day, they don't want to vote, or something happens. So I have to gather samples of the population. I need to think about, though, who am I going to sample? People who will vote in this election? I actually can't know that in advance. People who are eligible to vote? Well, that's better. But an even better choice would be likely voters. That's the closest match to our population of interest. But in order to use my samples of likely voters, I have to get a large and random sample. So, how do we take a sample from a population? Let's imagine that we own a zoo, and we know the population of the animals in the zoo. Our zoo has 15% owls, 3% unicorns, 31% squirrels, 19% bats, 24% frogs, and 8% bugs. It's kind of a boring zoo. And we can ask, what's the probability that a randomly selected creature, C, is any one of these animals? And so you can see in this formula that the probability of it being an owl, a unicorn, a squirrel, a bat, a frog, or a bug is 100%. Probability is 1, right? 1 out of 1, because we know if a creature's in this zoo, it's one of these. So again, we could ask, what's the probability that a randomly selected creature, C, is a squirrel? Well, we know that 31% of the animals in our zoo are squirrels. So the probability is 31%, or 0.31. So that's what we know about the total population. Let's say that we took a large randomly selected sample of the animals at the zoo. As long as that sample was large and randomly selected, that probability of an animal being a squirrel should still be 31%, or 0.31. The proportion should remain the same. As long as the sample is large and random, the proportion should pretty much line up between what we know about the whole population and what should show up in the sample. So here's an example, right? We know here, this list on the left, we know all these probabilities that a randomly selected creature is an owl, a unicorn, a squirrel, a bat, a frog, or a bug. That percentage expected in the large random sample should be the exact same, right? If this doesn't make sense to you, I would suggest you pause, rewind back to the beginning of us talking about probability sampling, watch it again, because now I'm going to move on to another example. If you're with me and you're like, I totally get it, then we will just move on. Okay. So in this example, this is a distribution of a bunch of random measurements of penguin flipper lengths. So we have a ton of penguins at another zoo, and we went and we measured all of their flippers. Okay? Well, not all of them. We measured a bunch of random penguin flippers. This graph right here is called a histogram. And this is the distribution of summary statistics. The x-axis, that's the axis on the bottom, is the flipper length in millimeters. And the y-axis is how many penguins had that flipper length. You can see from this that a ton of penguins, 24 of them, had a flipper length of 190 millimeters. Okay? And then you can see that, 24 had 190 millimeters, 14 had 186, etc. But we know in life, when we collect a bunch of random samples, that in general, there is a mean, a middle statistic, and that the rest of them kind of distribute around it. So you can see in this that we have this mean, and then these numbers are higher and higher, and then these are outliers, right? That on the edges, fewer and fewer penguins are down here towards 170, fewer and fewer are here towards 210. This creates this bell-shaped curve, and in life, this is just what always happens. We call this bell-shaped curve the normal distribution, and it uses this idea called the central limit theorem. The central limit theorem is a rule in statistics that says if you take a bunch of random samples from any population, like in this case, these penguin flipper lengths, and you add up all the values in the sample, the averages of those sums is going to be close to this normal bell-shaped curve. This works no matter what the original population looked like, as long as you have enough samples. The more samples you take, the closer it's going to be to bell-shaped. And this central limit theorem is really important because it helps us understand how statistics work and how we make predictions based on samples. So remember, we know that it's always gonna create this bell curve, okay? So here's this histogram again. And we can look at flipper length and figure out what percentage of penguins in the sample have that flipper length. So for example, 186 millimeters. 14 out of the total 146 penguins have a flipper length of 186 millimeters. 14 out of 146 is 9.6 penguins that have 9.6% of penguins that have the flipper length of 186 millimeters. And we can do this with all of these, okay? So we have, 170, 174, 178. We have all these different millimeters, and we can take the counts, divide those counts of each number of penguins with a particular flipper length, divide it by the total number of penguins, which was 146, and these percentages are going to help us predict what the distribution will look like in the entire population. So, if we select a penguin at random, what's the probability that that penguin is going to have a flipper length of 186 millimeters? The probability is 9.6%. Because remember, we calculated the number of penguins divided by that had 186 divided by the total, and this helps us to predict a particular outcome. If this is unclear, again, I would suggest you pause, listen to it again. If not, we will move on to the next stage of this. Okay, so we know that a probability distribution is a function that describes the likelihood or probability of a certain outcome. For example, if you roll the die, probability of rolling a 4 is 1 out of 6 if it's a 6-sided die. But in more complicated situations, the probability distribution is not so simple. And we will tend to use different kinds of distributions in order to understand. So, the sample distribution is the distribution of a statistic, like a mean or a proportion, that's calculated from multiple samples in a population. So let's imagine that I want to figure out the average height of all communication majors, the whole population of communication majors. So I take a random sample of 100 comm majors in one class, 100 in another class, 100 in another class, and I calculate the average, that's the mean, the average height for each of those random samples. The distribution of those means is called the sample distribution. They're all going to be a little different. Maybe the, COM 382 at mean height is a little taller than the COM 200 mean height. I don't know. But they still all should cluster around the mean of the population. We know that that is true. The larger the sample size, the closer the sampling distribution will be to a normal distribution. And regardless of the shape of the underlying population, the sample distribution is always going to be close to this normal bell curve. But how do I know if all these sample heights that I took are really accurate to predict the average height of the communication majors? So just like the animals and the penguin flippers, as long as we take multiple random large samples from the population, we will have statistics that cluster around the mean of the population parameter. So we're going to use those to make a good guess. So here's an example, okay, at this bottom one. So let's say that this doesn't really make sense for this, but this was like COM 200, COM 382, COM 303, and these were the distributions. They're all going to kind of build themselves around this mean of the population. And you can see they're all normally distributed, okay? That normal distribution is many samples from the population that cluster around this, okay? We see this in so many normal phenomenon. We also know in a normal distribution that the mean, median, and mode are all equal. The standard deviation determines how wide this curve is, and this helps us make statistical inferences. So this idea of standard error is really important. This is a way that we understand uncertainty in a sample statistic compared to the population parameter. This is how much we expect the sample mean to vary, okay? So in this example down here, the standard error is 5%. So our estimated result is 41%. 34% of the sample estimates will fall within one standard error below the population parameters. 68% of the sample, that's 34 times 2, yield estimates between 39 and 46 and so on. So this is hard, I know. Standard error, again, is a measure of the variability or the uncertainty in a sample statistic compared to the true population parameter. Standard error tells us how much we might expect the sample mean or proportion to vary if we were taking multiple samples from the actual population. So for example, again, imagine we're interested in figuring out the average height of all comm majors as a population. We get these random samples of 100 comm majors from different classes, and we calculate the mean height. The standard error tells us how much we can expect the sample mean height to vary from sample to sample, from COM 200 to COM 382 to COM 303. The formula for calculating standard error depends on the sample size and the variability in the population. Generally, the larger the sample size, the smaller the standard error. This means that larger sample sizes produce more accurate estimates of population parameters. Okay? Standard error is also important because we calculate confidence intervals from it, which is the range of values that the true population parameter is likely to fall within. So for example, if we calculate a 95% confidence interval for the population mean height, we can be pretty confident that the true population mean falls within that interval. Again, if this is tough, pause, rewind, listen to it again. I know this is hard if you haven't learned this before. So, the confidence interval and interval estimates. The odds of obtaining a sample statistic that will cluster closely around the population parameter are smaller. So we make interval estimates of population characteristics from 3 different values: the sample mean, which is our best single estimate, the standard error that's based on sample size, and the level of confidence that we want to achieve, which is usually 95% in the social sciences. Sometimes it's higher in the medical research. The confidence interval is a range of values that's likely to contain the true population parameter within a certain level of confidence. Confidence interval for a mean is the sample mean plus or minus the confidence level times the standard error. The margin of error is based on this confidence interval and helps us understand accuracy. So when we're thinking about this, the interval estimates are based on the best single estimate, the standard error, and the level of confidence. This confidence level and confidence interval are really important because they help us interpret the results of a study. The confidence level is a measure of how confident we are in the results, and it's expressed in a percentage, like 95%. I'm 95% sure that the results of this aren't just due to chance. So again, let's say we're estimating the average height of all the comm majors. That's the population. We take a random sample of these different comm majors and calculate the sample mean height. If we say that we want a 95% confidence level, that means we're 95% confident that the true population mean of height is falling within a certain range of values. The confidence interval is that range of values that is likely to contain that population parameter with a certain level of confidence. Margin of error is something we talk about quite often, and that is specifically used often. You'll hear it in campaign surveys or polls. When people take a survey, they might not always answer truthfully or accurately, which means that the results might be different than what might happen in reality. So the margin of error helps us to account for that discrepancy by giving us a range of value that the true answer is likely to fall within. So if we ask 100 people what their favorite ice cream is, and 60% of them say chocolate, the margin of error for this survey might be plus or minus 5%. So if 60 out of 100 people say chocolate is their favorite ice cream flavor, and our margin of error is 5%, we're pretty sure that between 55 and 65% of people actually prefer chocolate ice cream. The margin of error is influenced by both the size of the survey study, like how many people were in it, and the amount of variability in the answers. Generally, the larger a survey, the smaller the margin of error. Additionally, if everybody gives very similar answers to the survey questions, the margin of error will be smaller because there's less variability in the responses. Margin of error is a really important concept if you're looking at polling and election stuff. So again, if this was confusing, pause it, rewind. So we know that it's never going to be perfect. There's always going to be something lost between trying to figure out what's going on with the entire population and the sample that you drew. This is called sampling error, and it's the difference between the sample estimate and the population value being estimated, or how likely it is that the sample statistics match the parameter from the full population. There's always going to be sampling error, but we acknowledge it, again, by calculating the margin of error, which we just talked about, and it's a measure of how the results might be wrong from the truth. But we also have random sampling error. This is just the price you pay for not talking to everybody. It's the range that the answer likely falls between if we did talk, where would fall if we did talk to everybody. We try to keep this small, but we know it's always going to exist. What's more problematic is systematic error, like sampling bias, like overrepresenting some groups, types, characters, not having some languages, and it is not good, and we try really hard to avoid it. Okay, so that is all we're going to talk about probability. Again, if you're having a hard time, pause, rewind, listen to it again, read through the book chapter on this and listen to it again. It is a toughie. But the next thing we're going to move on to is talking about types of sampling. This should be hopefully easier. Okay, types of sampling. We have two major types: probability sampling and non-probability sampled. Probability sampling is randomly selected and is more likely to be representative of the population. Non-probability sampling is not randomly selected. So now we're going to talk about different types. All these types I'm going to talk about for a little while are going to be probability sampling. So they involve some sort of random selection. Simple random sampling is a form of sampling where every combination of cases has an equal chance of being selected. This is like pulling numbers out of a hat. It requires that you have a complete list of the population because you can't do a random selection if you don't have a complete list. So for example, let's say I had a list of all the communication majors and I wanted to measure their height. If I had a list of all of them and I just, closed my eyes and put my finger down and randomly found some people. In reality, this actually doesn't happen that often because even though it sounds simple, it's actually kind of hard because you need to have the list of the whole population. Another example of this is using a random number generator, and that could include a random digit dialing. So if people are doing phone surveys and they just have a random phone number that's generated and calls that person. It is very important that you don't mix this up with a random selection that we're going to talk about in experiments in a future module. So keep that in mind. Random sampling is about sampling. Systematic random sampling is a little bit different. You still need to have this list of the whole population, and then you choose an interval based on your total population that you're going to select every so many persons. So in this case, you're getting every third person. You're skipping 2 people. Maybe it's every 9th. It just depends, and I'll show you in a minute how to calculate this. This works best when a list does not have a pattern, like it's not ordered by height or something. It's easier to accomplish than simple random sampling, and it works a lot better than simple random sampling. So imagine that we had a study of comm majors and poli-sci majors, and our target population was 1,000 majors. And we knew that 682 were in communication and 318 were in poli-sci. Okay, so imagine that was the population. There were 682 comm majors and 318 poli-sci majors. And we want to have a sample size of 25. Picking that sample, we have to have the proportions relevant to the total population, okay? So target population is 1,000, our sample size is 25. We know that 682 comm majors out of 1,000 is that 68.2% of the total population are comm majors, and 31.8% of the total population are poli-sci majors. So we have to maintain those proportions in our sample. 68.2% of 25 is 17.05, and 31.8% times 25 is 7.95. So you would need to randomly select 17 comm majors and 8 poli-sci majors. Okay? So going back to this, when we're calculating that number of how many we need to count on, you have to follow a particular process, and there's a video on this that you can watch. But remember, you got to keep it proportional. Stratified random sampling, we're still under probability sampling. Sometimes in a study, there are subpopulations that matter to you, and so you will create stratum, which are groups or categories on a relevant variable. So maybe it's on region or grade level. And again, you got to make sure that the size remains proportional to what the population was. You randomly select within the strata, And by doing this, you're going to decrease your margin of error and increase representation in subgroups. But you have to know the population properties, and it is more expensive, so it really needs to be worth it, okay? So an example of this that you might want to do is if you're trying to do a nationwide survey and you want to make sure that you have representation from every state or representation from rural versus more urban states, though you could create those strata and select from within them. So again, you would create the stratum, you would ensure that the size remains relative and proportional, and then randomly select from within it. Multi-stage cluster sampling, sometimes just known as cluster sampling. It's almost always multi-stage. This is sampling that at every level, if it's multi-stage especially, is going to randomly select. So, for example, imagine that I'm interested in something going on with elementary schools. So I could randomly select at the states, all the different American states, then randomly select the cities in those states, and then randomly select an elementary school, and then randomly select from classrooms, and then randomly select students. At every stage, I'm randomly selecting, which is going to get me a better sample when they're nested within that. It's important when the subpopulation is important to your results. If the subpopulation isn't important, then you don't need to do it because it's really hard. To be honest, this is not done that often in communication research. You do see it in education research for sure, but it is important to know that it's just random at every level. So those are the major probability sampling types. There's some additional videos on this, so hopefully this will get stuck in your mind. We're going to talk about determining sample size. There's sort of this idea like bigger is better for sample size, and that is true, but there are diminishing returns, okay? So when we're trying to figure out what sample size we need, part of it is calculating how precise you want to be or how low you want your margin of error to be. And the absolute size of the sample determines the precision. The sample doesn't have to be huge to yield very precise results, depending on your margin of error. Also, your available resources, money and time, must be considered. So, most social science research, as we talked about earlier, uses a 95% confidence level and a 0.05 standard error to determine their sample size, but it really varies. There's a ton of online sample size calculators and power analysis calculators. There's a really good one from Qualtrics that is in the textbook that a lot of people use. So you can really calculate how many people do I actually need to talk to. Okay, next I'm going to talk about non-probability sampling. So this does not involve random selection. This means that this is only true for these people, and you cannot really do true statistical inferences on this sort of data. People still do statistical analyses on these. However, it's going to come with caveats that you're not actually, because you didn't engage in random selection, that your ability to argue that this is a representative sample is pretty weak. But sometimes it's okay if you're only trying to make arguments about some people, if you're only trying to make arguments about a specific group you can access. Non-probability sampling is usually done for practical reasons. Maybe only a subset of the population is accessible. Maybe it's impossible to construct an adequate sampling frame. Like there's no way to get a list of everybody in the population to create a sampling frame. Maybe the target population is unknown or hidden, or maybe you don't have enough money or time for a random sample. And it's also okay to do if the aim is to develop a holistic understanding of a group, or when cases are selected to advance theoretical understanding. In general, we prefer probability sampling, but it's not the end of the world if you can't. So one type of probability sampling is called convenience sampling. This is most appropriate in very early stages of research, and this is the typical sampling method that's used in experiments. And when we talk about experiments, you'll see why. It doesn't really matter if your sample in an experiment is representative of any particular population. This includes people or elements in a study because they're conveniently available. It's taking what you can get, voluntary asking your friends to participate. If you ever see a study where university students are participating in a study for extra credit, that is a convenient sample. This is the easiest way to sample, but it's also potentially the most dangerous because it's so vulnerable to self-selection bias that it's going to be pulling from the same kind of people over and over again. Purposive sampling is a non-probability sampling option that is better than convenient sampling, but it's still not as good as probability sampling. These samples are selected by the researcher because the researcher has determined that the participants reflect the characteristics that form the basis of the research that's needed. This is often done when the characteristic is unusual. So, for example, you're looking for people who are cancer survivors that play video games or something. You really have to try hard to find those people. You're not going to find those people probably if you just do a random sampling selection. It may broadly provide representative sample of that unique population, maybe. But because the researcher is always making judgments about who's involved, it's still not great. And to be honest, you don't see this that often. Snowball sampling is also a non-probability sample, and this is when someone who is participating in a study refers other people. This is incredibly useful if you're trying to reach people that are really hard to find, like, for example, people that are in some sort of group that's hidden, like a secret society. But it's just not going to represent the entire population. It's pretty common in social justice work, especially if you're gathering data on stigmatized groups. But if people just use it without a good justification, it's often pretty critiqued. Another non-probability sampling method that looks like probability sampling method is quota sampling. This is not commonly done in the United States, but it is pretty common in other parts of the world. So it starts with the identification of attributes of the population of interest. So imagine all Canadian university professors, and then selects participants with the attributes that match what you want. So if you know in the population of Canadian professors that a certain proportion of them are white men over the age of 50, you will purposefully sample people so that the demographics match the population of interest. So in this way, it's kind of like faking probability sampling, but because it does not involve random selection, it is not actually probability sampling. But you can imagine, because it's approximating the actual demographic profile of the regular population, some people think it pretty much works. And if your study is kind of low stakes, I don't know, you're trying to figure out what toothpaste flavors people like, this works totally fine. In how this works in practicality, let's say that you have a quota where 50% of the sample is going to be people who have a college degree and 50% of the sample doesn't have a college degree. You just keep inviting people to participate in your study until that particular proportion of people with college degrees and not is reached. So probably the time in your life that you think the most about sampling and survey work is when we have election polls for political campaigns, and margin of error is essential to understand how these work. So Political campaigns themselves and media organizations conduct surveys, polls, to try to figure out what the public opinion is and predict election outcomes. People really like to know these things before an actual election. Polling companies will survey a sample of likely voters to estimate the level of support for different candidates. So in a presidential election, a company will survey 1,000 likely voters. And let's say in that sample, they find 52% support candidate A and 48% support candidate B. But the margin of error, remember, that's the measure of the uncertainty in the poll results due to sampling error. It represents the range within which the true population is going to fall, given a certain confidence level, really matters. And remember, it's influenced by sample size, population size, and how variable the population is. In a sample of 1,000 likely voters, if they have a 95% confidence level, the margin of error is plus or minus 3 percentage points. So in this case, candidate A is more like between 49% and 55%, and candidate B is in between 45% and 51%. So it's possible that this particular election is much closer than it looks. So margin of error is absolutely essential to understand. Now, closer to an election, usually these polling firms will spend more money and get larger survey sizes in an effort to reduce the margin of error.